Hi, I'm Jeff Groh, and this is Differential Equations, Lecture 19. Today we're going to talk about series solutions. And in particular, the use of power series. The power series is a series of this form, an infinite sum of power functions. Here we have constants a sub k, and then this variable x minus the center c to some power k. One of the important questions that you might remember from Calculus 2 is, for which values of x does a power function converge? So let's back up and talk a little bit about the convergence of series. Intuitively speaking, a series is a sum. And in particular, we are interested in infinite series or infinite sums. In Calculus 2, you had quite a few tests for convergence for these various kinds of series, in addition to the divergence test. The divergence test said that if the terms of the series do not go to zero, then the series does not converge. This is the divergence test. If a sub n does not go to zero, then the sum does not converge. But there is one famous example that you need to be aware of where the terms do in fact go to zero and yet the series diverges. This is the famous harmonic series. You can prove the divergence of this series by either using the integral test or the p-series test. In this case, p is equal to 1, and that's a case for which p-series diverge. P-series diverge whenever p is less than or equal to 1, and converge whenever p is greater than 1. But you can easily integrate and prove that this diverges as well. You should also be aware of one can write this as negative 1 to the k or as negative 1 to the k plus 1. It doesn't matter. This is the alternating harmonic series. The alternating harmonic series famously converges. And you can easily prove that using the alternating series test. The terms in absolute value monotonically tend to zero, and that implies that this alternating series converges. It converges conditionally because in absolute value it reverts to the harmonic series which diverges. You should recall that there is such a thing called a Taylor series. And in particular, if f is infinitely differentiable, C infinity being the class of infinitely differentiable functions, let's say about some interval containing the center C, then the Taylor series of f centered at C is the sum. As k goes from 0 to infinity, you have the kth derivative evaluated at the point C divided by k factorial, x minus c to the power k. Now, this Taylor series doesn't always equal the original function f, but it does if the function f is analytic at the point C. Analytic meaning that the function f can be represented as a power series that has a positive radius of convergence centered at C. Famous examples of a Maclauren series. A Maclauren series is a Taylor series with center at C equals 0. A famous Maclauren series is that for e to the x, which is 1 plus x squared over 2 factorial plus x cubed over 3 factorial and so on, and that can be expressed as the sum as k goes from 0 to infinity of x to the power k divided by k factorial. You need to remember this. You should also remember the Maclauren series for sine x, which is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus and so on. This can be expressed as the sum as k goes from 0 to infinity, negative 1 to the k, x to the 2k plus 1 divided by 2k plus 1 factorial. In addition, cosine of x is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial and so on, which can be expressed as the sum as k goes from 0 to infinity, negative 1 to the k, x to the 2k divided by 2k factorial. These are both Maclauren series because they are centered at c equals 0. Also, these both have a radius of convergence equal to infinity. That means that these will converge for all x. The same can be said for the Maclauren series for the function e to the x. It converges for all x on the entire real line. You should be aware of the radius of convergence formula. That can be obtained from the ratio test. If you start with a series of this form, a generic power series, then by the ratio test we get convergence if the limit as k goes to infinity, the absolute value of a k plus 1 x minus c to the k plus 1 divided by a k x minus c to the k is less than 1. Note that x to the power k can be cancelled, numerator and denominator. Taking x minus c out of the limit, because it doesn't involve k anymore, we have the absolute value of x minus c times the limit as k goes to infinity of the absolute value of a sub k plus 1 divided by a sub k is less than 1. Dividing both sides by this factor, we get the absolute value of x minus c is less than the limit as k goes to infinity. When you divide by a fraction, you invert ak divided by ak plus 1. We'll define this expression to be r, the radius of convergence. As you know, you solve an absolute value inequality if a is bigger than 0 by negative a is less than x is less than a. Therefore, we have minus r is less than x minus c is less than r. Adding c to all three parts, we get c minus r is less than x is less than c plus r. The interval of convergence is the set of x values for which the power series converges. The interval of convergence will contain at least this open interval. What's left is to determine convergence or divergence at each of these endpoints where the ratio test fails. Recall that the ratio test fails when the limit of the ratio equals 1. That would be the case where we get equality here, and those would be the endpoints. Let's look at an example. Suppose we have the sum, as k goes from 1 to infinity, of x minus 3 to the k divided by k. The center here is 3, and the radius of the convergence is going to be the limit as k goes to infinity of the absolute value. In this particular instance, a sub k is 1 over k. It's the coefficient of the x to the power factor. And so we're going to have 1 over k divided by 1 over k plus 1 in absolute value. Clearly, the radius of convergence is 1. That means from the center we go 1 unit to the right and 1 unit to the left. The interval of convergence will contain all points from 2 to 4. Notice that I said it contains. This is kind of a backward subset. It means that this is a subset of the interval of convergence. It may not equal the interval of convergence. To be sure, we need to test the endpoints and see if we get convergence or divergence at each of the endpoints. First, let's test convergence at x equals 4. If x is equal to 4, we get the sum as k goes from 1 to infinity. 4 minus 3 is 1. 1 to the power k is 1. And we end up with 1 over k. This is the harmonic series which diverges. So we know we do not include 4 in the interval of convergence. Now let's test x equals 2. If x is equal to 2, we get the sum as k goes from 1 to infinity. 2 minus 3 is negative 1. We get negative 1 to the k divided by k. That is the alternating harmonic series, which converges. It follows then that the interval of convergence is equal to the half open, half closed interval, including 2, but excluding 4. I'd like to look at a very simple example where we can solve a differential equation using power series. Suppose that our differential equation is y prime equals y. Now we already know that the solutions are of the form y is a constant times e to the x. Those are functions with derivatives equal to themselves. So we know the answer to this problem. Here's how we're going to approach it, however. We're going to assume that the solution is analytic. What does it mean to be analytic? It means that this solution is a function that has a power series representation, which means that the function may be placed into the form the sum as k goes from 0 to infinity, a sub k. Let's assume that it's centered at 0, and so it's a sub k times x to the power k. If that's true, then this solution has the form a0 plus a1x, and so on, higher and higher terms after that. What does the derivative look like? The derivative of the first term is 0 because the derivative of a constant is 0. That's our first lesson. When we calculate the derivative of a power series like this, we lose the first term. Because the first term was constant, its derivative is 0. On all of the other terms, we use the power rule. K, a sub k, x to the k minus 1. Plugging all of this into the differential equation, we get the sum as k goes from 1 to infinity, k a sub k x to the k minus 1 equals the sum as k goes from 0 to infinity, a sub k x to the k. Now, one fundamental fact about power series is if one power series is equal to another, then their corresponding coefficients must all be equal. However, you have to equate corresponding coefficients, and to do that, we're going to re-index the sums to make that easier. I would like this exponent, k minus 1, to be the same as this exponent. To do that, I'm going to change the index to a new index. Technically, the index is kind of a dummy variable since it does not appear in the answer. We can write this as a0 plus a1x plus a2x squared, and so on, where k does not appear in any of those terms. K is a device for expressing the sum of all of those terms. It doesn't matter what you call it. We could have called this L or M or I or J. Same thing over here. I'm going to give it a new name for now. I'm going to call it capital K. Capital K is going to be old k minus 1, which also means k plus 1 will be equal to the old k. I'm going to use these two facts to re-index the sum on the left. The new k is going to start where the old k was equal to 1. If the old k is 1, the new k starts at 0. As the old k goes to infinity, the new k also goes to infinity. The old k gets replaced by k plus 1, and x to the k minus 1 is going to be x to the new k. That's going to be equal to the sum as k goes from 0 to infinity, a sub k x to the k. Now both sums have the same power on x. And again, because this k is really a dummy index, a dummy variable, we can just pretend that the new k is the same as the old k. We can just rename it. Now, coefficients of x to the power k on one side will equal coefficients of x to the power k on the other side. We deduce then that k plus 1 a k plus 1 is equal to a sub k, which implies the new index ak plus 1 is going to be the previous index divided by k plus 1. This is called a recursion relation. We determine the further indices down the line by the previous indices. Since an index is completely determined by the previous index, there is no previous indexed a0, which means a0 will be arbitrary. We'll just let it be an arbitrary variable. a1 is what you get when you plug in k equals 0 everywhere inside of the recursion relation. a1 is going to be a0 divided by 1, which is the same as a0. a2 is what you get when you plug in k equals 1 into the recursion relation. That's going to be a1 divided by 2. But keep in mind, a1 is equal to a0. So this is a0 divided by 2. a3 can be found by placing k equals 2 into the recursion relation. That's a2 divided by 3. But a2 was a0 divided by 2. So replacing a2 by a0 divided by 2, we get a0 divided by 3 times 2. It's better if you don't simplify at this point. Leave things multiplied out like this. You'll be able to see what goes on a little better if you do not simplify. A4 is going to be A3 divided by 4 according to the recursion relation, but A3 is A0 divided by 3 times 2. So A4 is going to be A0 divided by 4 times 3 times 2. You should be able to see what's going on now. We're getting factorials in the denominator. We can deduce now the form of the kth term. Instead of a recursion relation, we can now write down A sub k is going to be A0 divided by k factorial. Here we have A3, A0 divided by 3 factorial. A4 is A0 divided by 4 factorial, and so on. This is said to be a closed form for the coefficients of the power series. We deduce then that the original function y is the sum, as k goes from 0 to infinity, of A0 divided by k factorial times x to the power k. We can rewrite that as A0 times the sum, as k goes from 0 to infinity, of x to the k divided by k factorial. Given our previous discussion, you should be able to recognize that power series. That's the power series for e to the x. We deduce then that our solution is A0 times e to the x. Note that the constant of integration is the coefficient A0. Let's think for a moment about the solution process. We started off by assuming that the solution takes the form of a power series. That is, the solution is some analytic function. Taking the derivative of an arbitrary power series, we plugged what resulted into the differential equation. In order to equate coefficients, we had to first re-index one of the series. After re-indexing, we equated coefficients and obtained a recursion relation. Once we had the recursion relation, we explored that to find a closed form for the coefficients for the power series describing our analytic solution. Once we had that, we wrote down the answer. Now, I know what you're thinking. We just found a very complicated way to solve very simple problems. However, I promise you, there is a good reason to study this method. In particular, we need what is called the method of Frobenius, which we're leading up to. The method of Frobenius is necessary for solving certain partial differential equations. Partial differential equations can model the diffusion of heat or waves. The wave equation or the heat equation are important in solving or modeling solutions to a lot of applied problems. The solution of those equations requires this method of Frobenius that we're going to derive. This method of Frobenius uses power series to construct certain functions and there really is no other way. We're going to need to know this method of Frobenius. To get to the method of Frobenius, we have a little more theory to develop. But before we do that, I want to do some very simple examples that add to the techniques that we've already seen. So I want to look at the example y prime equals x times y. I know it's separable, linear, first order, homogeneous, any number of adjectives you could apply to this, and it's very easy to solve by other means. We are going to solve this using power series. We're going to assume that the solution has the form, the sum as k goes from 0 to infinity, a sub k, x to the k. Power series always start at k equals 0 or higher. They don't start at k equals -1 or -2. Those would give you singularities. If this is y, then y prime will be the sum as k goes from 1. Remember, we lose that first term, which was constant, k, a sub k, x to the k minus 1. we're going to plug these two things into the differential equation. When we do, we'll have the sum as k goes from 1 to infinity, k, a sub k, x to the k minus 1 equals x, times the sum as k goes from 0 to infinity, a sub k, x to the k. You can see that we get one more factor of x, which can be added on here. It's at this point that we need to re-index the sums. If we set new k plus 1 equals the old k minus 1, I want to get k plus 1 instead of this k minus 1 here, then notice that k plus 2 will be the old k. We'll have the sum as the new k. If the old k starts at 1, by the way, the new k is going to be the old k minus 2, moving this 1 over. If the old k starts at 1, the new k will start at negative 1. Is that going to be a problem? We'll find out. As the old k goes to infinity, the new k also goes to infinity. The old k gets replaced by k plus 2, and we'll have x to the new k plus 1. Now we see that starting at negative 1 here won't be a problem, since it won't introduce a singularity. At big K equals negative 1, that gives us x to the power 0, which is as low as we can go, x to the power 0. We can't go to x to the power negative 1. That's why this series can't start at negative 1. But this series can. That's going to be the sum as k goes from, well, this series could start at negative 1, just can't start at negative 2. 0 to infinity, a sub k, x to the k plus 1. Before equating coefficients, we have to take into account the fact that this series begins at k equals negative 1, where this series begins at k equals 0. The k equals negative 1 case has nothing corresponding to it over here. So its coefficient, the negative 1 case, that's going to be 1 times a sub 1. That coefficient of this power of x must equal 0, since it has nothing corresponding to it on the other side. We see that a sub 1 is 0. This will be important in determining the solution to the differential equation. When k is bigger than or equal to 0, then both series come into operation, and we get the recursion relation k plus 2 a k plus 2 equals a sub k. We find a k plus 2 is a sub k divided by k plus 2. You can see then that coefficient doesn't determine the next coefficient, it determines the coefficient 2 down the line. There's kind of an every other one principle here. Notice that since a1 is 0, if we plug in 1 here for k, we'll get 0 here, a3 will be 0 divided by 3, or 0. Similarly, if we plug in k equals 3 here, we'll have a5. a5 is going to be a3 divided by 5, and that is also 0. Going on down the line, you can see that all odd coefficients will be 0, because the first odd coefficient is 0, and then all coefficients are determined by this every other one principle. To solve this problem, we have only to determine the even coefficients. To this end, note that a0 will be arbitrary. a2, according to the recursion formula, will be a0 divided by 2. a4 will be A2 divided by 4, making this substitution, we'll get A naught divided by 4 times 2. A6 is going to be A4 divided by 6. And knowing A4, we know we'll have A naught divided by 6 times 4 times 2. So, how are these coefficients changing? Notice we can take a 2 out of each of these and rewrite this as A naught divided by, we'll take a 2 from each of these, that's going to be 2 cubed. What's left over is going to be 3 times 2 times 1, which is 3 factorial. Notice that this is 2 times 3. A4, on the other hand, will be A naught. We can take a 2 from each of the factors in its denominator, and what's left over is 2 times 1, or 2 factorial. We finally have A sub 2k, 2k, is A naught divided by 2 to the power k times k factorial. That means our solution is the sum, as k goes from 0 to infinity. Keep in mind that all odd coefficients are 0. So we have to find a way to express only these even coefficients. That's going to be A naught divided by 2 to the k factorial, x to the 2k. We're only getting even powers of x in the solution. We know we can factor the A naught out, but how can we see what this solution is? We'll have a sum as k goes from 0 to infinity. One way to see what this is to note that sure you have this 1 over k factorial. Everything else is going to be to the power k. I'll have x squared over 2 to the power k. You might be able to see then that this is A naught e to the power of x squared over 2. Yes, we could have come to this conclusion much more easily. The original differential equation was dy dx equals xy, which can be separated as 1 over y dy equals x dx, which we could then integrate. We'll have the natural log of the absolute value of y equals x squared over 2 plus a constant of integration, and that gives you y as a constant times e to the x squared over 2. A much quicker way to arrive at the solution. However, this problem illustrated another important principle that is necessary in solving these differential equations, and that is, sometimes when you re-index, the indices don't match. That initial index doesn't match, and you have to account. In our case, we had to account for k equals -1 separately from k greater than or equal to 0. And that gave us A1 equals 0, and hence all of the odds after that were also 0. So that's another element of the solution process that needs to be looked after. To further develop the theory, we have to introduce some terminology. Consider the differential equation y double prime plus p of xy prime plus q of xy equals 0. In this differential equation, if p and q are analytic at x naught, we call x naught a regular point. Otherwise, x naught is called a singular point. So if these coefficients are smooth, really smooth, more than C infinity smooth if they're analytic. If these coefficients P and Q can be expressed as functions having a power series representation that has a positive radius of convergence, then x0, centered at x0, then x0 is a regular point. Otherwise, it's called a singular point. Remember that if a function can be represented as a power series, then its derivative can also be represented as a power series and having the same radius of convergence. That means that if a function is analytic, then it must be differentiable. Not only that, but since the derivative is a power series having a positive radius of convergence, the derivative is also differentiable, and so on and so forth, which means any function that is analytic is automatically infinitely differentiable. These functions have derivatives of all orders. Functions that are analytic are very, very smooth. This also means that any point where a function is not continuous is certainly a point where it is not regular. It has a singularity there. Let me give you an example. Suppose I have the differential equation y double prime plus 1 over x minus 1 y prime plus 1 over xy equals 0. The singular points here are x equals 0 and x equals 1, because we have places where we have vertical asymptotes, because the coefficient functions have vertical asymptotes there and are not continuous. They are singular there. I should be just a little more careful than I'm being here. If I have sine of x divided by x, this function satisfies the following fact. The limit as x goes to 0 of sine x over x, notice that if you just plug 0 in, sine of 0 is 0, and we'll have divided by 0. But in the context of limits, 0 divided by 0 means more work. And in particular, this is a L'Hopital's rule case. You could easily show using L'Hopital's rule that this limit is equal to 1. If this function, sine x over x, has what is called a removable discontinuity, we can patch the hole in the function at x equals 0 by defining that function have a value of 1. So this function has a removable discontinuity at x equals 0. If that's the case, we're still going to say that 0 is an ordinary point, even if the functions technically aren't smooth there, they're not continuous, we have a discontinuity. If the discontinuity is merely removable, we'll go ahead and remove it and declare the point to be a regular point. At regular points, we have no trouble representing solutions as analytic functions or as power series. It's at singular points where there's an issue, and in particular, the method of Frobenius only works at a certain kind of singular point. Yes, we have another term we need to define. We call x0 a regular singular point I know that seems like a contradiction in terms. If x0 is a singular point of P and Q, where we're looking at differential equations of the form y double prime plus P of x y prime plus Q of x y equals 0, but x minus x naught P of x and x minus x naught squared Q of x can be made analytic. by patching the hole at x equals x naught that must exist. In other words, provided we can eliminate the non-analyticity by multiplying by one factor of x minus x naught onto p and two factors of x minus x naught onto q, then we have a regular singular point. If the point is not a regular singular point, but still a singular point, we call it an irregular singular point. Note, at a regular singular point, x naught, these numbers, p naught, the limit is x goes to x naught of x minus x naught p of x, and q naught, which is the limit as x goes to x naught of x minus x naught squared q of x, must exist as finite limits. These are the values that patch the removable singularity holes at x naught once we multiply by one factor of x minus x naught onto p and two factors of x minus x naught onto q. We're now ready to introduce the method of Frobenius. The method of Frobenius only works for regular singular points. So we'll say let x naught be a regular singular point. That means there must be some kind of non-analyticity involved in our solutions. So at the point x naught, since the solution must have some kind of singularity because the coefficients of the differential equation do, we need to introduce that singularity from the start. And here's how we're going to do it. We're going to set y to be x minus x naught to the power of r for some real number times some analytic piece. So on this piece, sum will go from 0 to infinity, a sub k, x minus x naught to the power k. All nice and good there. R is not assumed to be an integer or a whole number. It could be negative. It could be negative 1. If this is negative 1, we're going to have a singularity at x naught. If it's equal to 1/2, its derivative might have a singularity at x naught. You can see then that we can introduce problems by putting on these very limited factors. The solution will have the form, the sum as k goes from 0 to infinity, a sub k, x minus x naught to the power of k plus r, adding these r factors of x minus x naught onto those k factors inside of the series. We're going to assume that our solutions have this form. With solutions of this form, it's no longer clear that when you take the derivative that you lose a term. If r is equal to 1/2, you're not going to lose a term. So we're going to take the derivative, and it's still going to start at 0 and go to infinity. We'll have k plus r, a sub k, x minus x naught to the k plus r minus 1. Also, we can't assume the second derivative loses any terms either, so it's going to start at 0 and go to infinity. K plus r minus 1, a sub k, x minus x naught to the k plus r minus 2. We're going to plug all of this into the differential equation and see what happens. Plugging all of these into the differential equation, we get 0 equals the sum as k goes from 0 to infinity, k plus r minus 1, a sub k, x minus x naught to the power of k plus r minus 2, plus p of x, the sum, as k goes from 0 to infinity, k plus r a sub k, x minus x naught to the power of k plus r minus 1, plus q of x times the sum, as k goes from 0 to infinity, a sub k, x minus x naught to the power of k plus r. Now, from this whole thing, I'm going to factor x minus x naught to the power of r. That's going to take all of these r's away. R factors of x minus x naught are going to come out. And I'm going to divide that off. Second, on this term, I'm going to take one factor of x minus x naught to join p of x, and two factors of x minus x naught to join q of x. That's going to give us x minus x naught here, and we'll have to take one factor away, giving us k minus 2 here. And x minus x naught squared here, and I'm going to have to take 2 away from here in order to put these two out front here. Before doing anything else, I'm also going to take out x minus x naught to the power negative 2, since all of those match. We can bring that out and cancel it off. It's at this point I want to take the limit as x tends to x naught. When we take the limit as x tends to x naught now, if k is bigger than 1, then x minus x naught to the power k will go to 0. Only the k equals 0 term will yield something. If we take the limit as x goes to x naught, almost all of these terms are going to go away. The only one that survives is the k equals 0 term. And what is that? That's going to be r times r minus 1 times a naught. On the next line, we've seen that this factor, x minus x naught p of x, in the limit tends to the number p naught, which patches the hole from the removable singularity that you have left over after multiplying by the factor x minus x naught. But you also have this other factor, k equals 0 here, and that gives you r times a naught. All the other terms have limits equal to 0. And then, on the last line, you'll have q naught times a naught. This gives us a quadratic equation for the variable r. That means that not all values of r are going to work. Only up to 2 distinct values of r will give you solutions using the method of Frobenius. We have the following equation. If we factor a naught out and cancel it off, 0 equals r times r minus 1 plus p naught r plus q naught. P naught and q naught are pretty easy to find. We just calculate the appropriate limits, plug them into here, and solve this quadratic equation for r. That allows us to construct the appropriate solutions using the method of Frobenius. Let's give this a shot. I'd like to give you an example that arises in connection with diffusion problems. Often there's another constant here in front of the y, but I just want to keep things simple. We see that x naught equals 0 is a singular point. Is it a regular singular point? Provided those numbers p naught and q naught are finite real numbers, that means we will be able to patch the holes by multiplying by x minus x naught onto p and x minus x naught squared onto q, all we have to do is calculate p naught and q naught. This will be the limit as x goes to the singular point 0, x minus 0 p of x. P of x in this case is here. That's the limit as x goes to 0 of x times 2 divided by x. Well, that limit is 2. Q naught is the limit as x goes to 0 of x minus x naught squared, q of x. Q of x is just 1. As x goes to 0, this whole thing goes to 0. It follows then that our equation is going to be 0 equals r times r minus 1 plus 2r plus 0. We can simplify this by factoring an r out. If you bring this r out and this r out, all that's left is r minus 1 plus 2, which is r plus 1. The two values of r that are going to work here are r equals 0 and r equals negative 1. R equals negative 1 gives you a singularity at x equals 0, which is kind of expected because we have a singular point at 0. However, r equals 0 means x minus x naught to the power r is going to be 1. 1 times an analytic function is what your solution will look like. So we expect there to be one solution that is analytic, the one corresponding to r equals 0, and another solution that has a singularity at r equals 0. We're going to see both of those pretty soon. We have two different values of r that we can choose, and we expect to get two linearly independent solutions by which we can construct the general solution by arbitrary linear combinations. Which of those two solutions you get depends upon the value of r that you work with. However, for sake of definiteness, the method of Frobenius usually assumes that you choose the larger of the two. In this case, we'll choose r equal to 0, which means that y is going to be x minus 0 to the power 0. This is our singular point. This is our r value, times the sum as k goes from 0 to infinity, a sub k, x to the k. Again, I'm assuming the center is 0 because our singular point was 0. This is just 1. We're assuming our solutions are just some analytic function of the form the sum as k goes from 0 to infinity, a sub k, x to the k. Now, since r was equal to 0 in this case, when we take the derivative, we do need to pay attention to start at k equals 1. We are going to lose a term here. We'll have k, a sub k, x to the k minus 1, and y double prime will be the sum as k goes from 2 to infinity, k times k minus 1, a sub k, x to the k minus 2. Plugging these into the differential equation, we have 0 is the sum as k goes from 2 to infinity, k minus 1 a sub k, x to the k minus 2, plus 2 divided by x times the sum as k goes from 1 to infinity, k a sub k, x to the k minus 1, plus the sum as k goes from 0 to infinity, a sub k, x to the k. Notice that this x can cancel one factor of x here, giving us x to the power k minus 2. This term also has an x to the k minus 2, and that means this term is the odd one out. We only need to re-index this one sum to match the exponent of x to the other two series. Making the change of index, the old k is going to be a capital K minus 2, so the capital K will be the old k plus 2. That means this sum can be replaced by the sum as the new k. If the old k started at 0, the new k is going to start at 2. Still going to infinity. A sub k minus 2, x to the k minus 2. The old k gets replaced by the new k minus 2. Now all three terms have x to the same power. However, the first series and the last series begin at 2, whereas the middle series begins at 1. So we have to treat the k equals 1 case separately. All coefficients on the left-hand side are 0. When k is equal to 1, we get 2 times 1 times a sub 1. That implies then a sub 1 is 0. If k is bigger than or equal to 2, all three series come into play. We get 0 equals, here we have k times k minus 1 a sub k plus 2k a sub k plus a sub k minus 2. We can combine these two terms and then solve for a sub k. The first two terms have a common factor of k times a sub k. If I take the k a sub k out, I'm left with k minus 1 plus 2, which is just k plus 1. If we move to solve for a sub k, this term will have to go to the other side, becoming minus, and we'll divide by k times k plus 1. This gives us our recursion formula. It has an every other one principle. Each coefficient is going to be determined by the coefficient 2 before. Since a sub 1 is 0, a sub 3 will also be 0, and a sub 5 will be 0 as a consequence. You can see that a sub odd are all going to be 0. The only question left is, what happens to the even values, a sub even? We determine the even values by hook or by crook. We will, of course, assume that a naught is arbitrary. What is a2? a2 is what you get when you plug in 2 for k. That's going to be minus a naught divided by 2 times 3. And again, don't bother simplifying these. It's just going to confuse matters. What is a sub 4? Plug in a 4 here, you get minus a2 divided by 4 times 5. But remember, a2 is minus a naught, so we'll get a positive a naught divided by 2 times 3 times 4 times 5. What does a sub 2k look like? This is 2 times 2. This is 2 times 1. I think you can see that what you're going to get is negative 1 to the k a naught divided by, if this is 4, we had 5 factorial, it's going to be 2k plus 1 factorial. That implies that our solution is going to be the sum, as k goes from 0 to infinity, of negative 1 to the k a naught divided by 2k plus 1 factorial times x to the power of 2k. Remember, all the odd coefficients are 0. We only get even powers of x left over. The series that we obtain here, which is a solution, it's one of our two solutions to this differential equation, you might be able to recognize almost. It almost looks like the power series, the Maclauren series, for sine of x. The only thing is, Sine is an odd function and has only odd powers of x. This function has only even powers of x. It's as though one factor of x has been canceled off from each term in the Maclauren series for the sine function. This function is in fact a naught sine of x divided by x. This a naught can just be dealt with later as one of our constants. We'll have c1 y1 plus c2 y2. You might object. This function looks like it's singular at x equals 0, but in fact we saw earlier that this function tends to 1 as x tends to 0. The singularity can be removed by just patching the hole. And in fact, this power series does in fact have a radius of convergence equal to infinity, so it will exist and be analytic everywhere. After you remove the singularity here, you end up with an analytic function, one representable by a power series having a positive radius of convergence, in fact, infinite radius of convergence here. So if this is one of our solutions, how do we find the second solution? You can either go back and choose r equals -1, or you can use the method called reduction of order, which allows you to solve these second order equations by assuming the solution has the form some function u times y1, or I could just tell you y2 ends up being cosine of x divided by x. You can see this function has a problem at x equals 0. It's more serious than this one. This one you can patch the hole. This one you can't, because as x goes to 0 in the numerator, cosine goes to 1. But the denominator will go to 0. So this function has a singularity at x equals 0. That is important for applications. When you're applying this theory to problems involving diffusion or the wave equation, you're going to need to keep in mind nature abhors singularities, things that go off to infinity, like this function here, well, more like this. As you go to 0, it's going to be unbounded. It's going to have this singularity. That doesn't happen in nature. So on applied problems, we would say this solution, it is a mathematical solution to the differential equation, but it's not a physical solution because of the singularity at x equals 0. So we're going to toss that solution out. This is very common in applied problems. This solution's okay. This solution not so much. This theory is going to be very important in analyzing something called Bessel's equation and constructing the so-called Bessel's functions when you study partial differential equations. Also, I would like to indicate something else. We could have taken a shortcut here that might have made things a little easier for ourselves. We could have followed the method of Frobenius until we got r equals 0 or -1. This r equals 0 doesn't give us much new, but the r equals -1 does. What if we had assumed that the solution is of the form u divided by x for some analytic function u? That implies, let's forget the subscript for now, that y prime is u prime over x minus u over x squared, recalling that the derivative of 1 over x is -1 over x squared. And y double prime is u double prime over x minus u prime over x squared when you take the derivative of 1 over x here. When you take the derivative of u over here, you get one more term of this form, and then plus 2u over x cubed, because the derivative of 1 over x squared is -2 over x cubed. If we plug these things into the differential equation, we get 0 equals u double prime over x minus 2u prime over x squared plus 2u over x cubed plus 2 over x times u prime over x minus u over x squared plus u divided by x. Combining like terms, you can see that we are going to have this term and this term exactly cancel out. In addition, this term and this term exactly cancel out. That leaves only these two terms left. We can multiply both sides by x, and that reduces to a very simple differential equation. The differential equation on u is 0 equals u double prime plus u. This has characteristic equation, lambda squared plus 1, which gives you lambda equals plus or minus I. So alpha is 0, beta is 1. That gives you u is c1 cosine of x plus c2 sine of x, and hence, since y is u divided by x, we get c1 cosine of x over x plus c2 sine of x over x for our solutions. Okay, that's way better than the method of Frobenius as we implemented it here. And the thing is, this shortcut doesn't always work out quite so nicely as it did here. I just thought it would be only fair to make you aware that there are shortcuts sometimes once you know the values of r that are possible.